So the AlphaFold project actually started in a hackathon. I think this is like testament to the power of hackathons, an internal hackathon within the applied group, which is the group that I was helping to run at DeepMind. And, I think that really is testimony to the fact of what you can do in a couple of days of concentration. We let the people in the team work on anything they wanted to work on. We did 2 days, cleared the decks, did it just before the weekend so people could kind of carry on working through the weekend. And 2 guys, Hugo Pedidones and Marek Barwinski, whose names should forever be remembered, decided that they would go after protein folding in a couple of days.
Welcome back to the Middle Tech Podcast. You've got Logan Jones here, and today I'm very excited to release a recording from our interview during our July AI Meetup with Steve Crossan. So if you did not see any of the posts promoting this event, Steve Crossan is one of the founding members of AlphaFold from Google's DeepMind. He also spent years and a good portion of his career at Google working on things like Gmail, Google Search, and Google Calendar. If you've ever heard of those tools before. So somebody with a ton of experience, and pretty wild that we had him here in person in Lexington. He was willing to give his time to speak to the group of about 50 or 60 people that showed up to that event. So if you have not been to one of our AI meetups before, we would encourage you to come. We'd love to see you out there. It is not meant for only experts or people that know to code or are currently using it. You can be a complete beginner, and I feel like you'd still get a lot out of coming to the meetup. It's also just a great time. We have food and drinks beforehand, and then people typically stay and hang out after. So if you want to stay up to date on attending those meetups, make sure you subscribe to our newsletter. That's where I send out notifications about new events. That's in the show notes below. And I'm not going to give much of an intro to Steve here because in the recording, you'll hear me kind of read his bio, and it is very impressive. So I hope you guys enjoy this episode. I know this was one of my favorite conversations I've had on this podcast. I say that every now and then, but this one truly ranks up there in at least the top 5 for me. One of the most in-depth, interesting conversations we've had around an emerging technology like AI and its intersection with biotech. So excited for you guys to tune in. Would love to hear what you think. Before we get started, let's just get a quick word from our sponsors. Before we highlight our sponsors, we'd just like to state that the views and content shared on this platform do not necessarily reflect those of our show sponsors. That being said, Middle Tech is supported by KY Innovation, the Kentucky Cabinet for Economic Development's Office of Entrepreneurship. KY Innovation exists to support and develop Kentucky's startup ecosystem, and we are proud to be supported by an organization whose mission aligns so closely with ours. If you are a founder building in Kentucky, you need to check out the resources that KY Innovation has to offer. You can find more information by clicking the link in our show notes or going to kyinnovation.com. Before we get started here, I want to make sure that I give a big shout out and thank you to Professor Brent Seals and Randall Stevens for making this happen tonight. It was kind of a great coincidence that Steve was here in town in Lexington, so it's a real treat that we get to have this talk in person. Steve has an incredible background that I'm really excited to get into. So first off, just wanted to start with a thank you to you guys for making this happen. Yeah, absolutely. Round of applause. And Steve, this is your first time in Lexington.
This is my first time. It's a pilgrimage.
A pilgrimage.
I've been planning to make for about 15 years.
And you got your whole family with you.
Yes, the whole gang is here.
And you said your son is working with Brent at his lab?
That's Ned right there. Yep, and he's doing a couple of weeks with Brent in the lab, in the Educe lab.
Awesome. Love it.
That's cool stuff.
Well, for those who are new to our AI meetups, we try to host these each month just to bring together people, whether you're in the space, you're building something, whether you're just interested in the space, or whether you're completely new to it. We want to bring people together to have conversations around this technology that is going to be shaping our future from here on. So this is a little bit different of a format. We typically just let somebody get up here and do a presentation, have a talk. When we knew that Steve was coming in, we wanted to do something a little bit different and have a conversation that we could put out on our podcast feeds. So if you're not familiar with Middle Tech, we have a podcast we've been running for about 6 years. So you'll be able to hear this conversation on there as well. But to kick off our conversation with Steve, just want to do a quick intro here with some of his background. So Steve is a veteran product leader and investor at the cutting edge of AI and biotech. So Steve spent a decade at Google shaping products that you may have heard of, things like Google Maps, Gmail, Google Search, and then founded the Google Cultural Institute, putting things like Nelson Mandela's archives online for the world.
In 2016, he became a founding member of DeepMind's AlphaFold team, which is what a lot of our conversation will be about today, helping crack the 50-year protein folding problem and paving the way for research that later earned that team the Nobel Prize in chemistry. After DeepMind, Steve served as the VP of AI and machine learning at GSK, building out an AI-powered drug discovery unit, and today he's an operating partner at deep tech venture capital firm DCVC, advising startups at the intersection of machine learning and life sciences. And he recently founded Dayhoff Labs, applying generative AI to chemical biology. So we're thrilled to have him here in Lexington to talk AlphaFold, DeepMind, AI-driven biotech, and more. So Steve, thank you so much for joining us.
Delighted to be here.
Awesome. All right. So Steve, for those who it's their first time meeting you, first time hearing your background, can you just kind of walk us through how you found yourself working at the cutting edge of AI and science? What were some of the pivotal moments that kind of got you to this moment in your career?
Great question. So I think at one level, this is something that I've always been interested in, actually, even before my graduate studies, which is a horribly long time ago now. I got into computer science actually originally through reading a book, which probably many people have read here, called Gödel, Escher, Bach by Douglas Hofstadter.
Can you say that again?
Gödel, Escher, Bach by Douglas Hofstadter, a great book, like one of the classics of AI, written in the late 70s, but like just an incredible book with all kinds of ideas and information, not just about AI, but also about kind of science in general and about biology and about life. And that was really kind of, for me, the genesis of what made me want to get into computer science and eventually into artificial intelligence. And during my grad studies, I studied for a PhD at the University of Sussex in AI, which I didn't finish because I went to start a company. But during that time, we very much had a kind of biological approach to AI. So we were thinking really about embodied robots. What is it about a situated robot that makes that an interesting environment for learning? So this was kind of really kind of quite ahead of its time. And I was convinced at that time that there is something about biology and the difference between biology and chemistry, which is kind of fundamental to this idea of complexity in the universe, complex systems capable of behavior, capable of synthesis, capable of computing information, that we really need to understand. And so I've kind of been interested in that ever since. And so when I was at Google and I got the opportunity to move over to DeepMind, so this was in 2014, 2015, kind of before they were famous almost in some sense, before the whole field was famous, then I took it. In fact, I kind of hustled my way in. I just went and sort of squatted in their building and tried to be helpful to them until they said, why don't you come and do some stuff with them? Because I was convinced that this is going to be like important stuff for the future, and I really wanted to kind of get back into that, and especially get back into that intersection of AI, but also AI in the context of fundamental science as well.
Was there an early application that you experienced early, either in academia or your career, that really just got you super passionate about it and said, I definitely want to continue to be in this space?
I think the big one which has unlocked everything else was actually getting into AlphaFold, which I guess we'll come on to that in a bit. Before that, I spent my PhD years working on robot football, on teaching very small robots who are like about this big robots with like two-wheeled robots to move a ping pong ball around a small football field in simulation. And this was like these things had maybe like 50 neurons that you could program on there. But we managed nonetheless to teach these things to kind of control the ball. They were playing one-on-one football. Soccer, by the way, not football.
Thank you for
one-on-one football, and getting them into the goal, and it kind of worked. And there was all kinds of sort of really interesting stuff about embodied robotics at that time. There was a thing called the Octopod, which you should go look up from that time, which became very influential. And just that idea that you could take these embodied machines in simulation, but also in reality, And with these very, very simple architectures, you could create very complex behavior. I think that was one of the first moments when I thought, there's a lot that's interesting here.
And that was, can you give us a timeline on when that, remind us?
So this is like late 90s, early 2000s.
Okay. And so, wow. So, and I'm curious from your perspective, you're somebody that's been in this space and you've been around artificial intelligence kind of before the rest of us really got to experience the power of artificial intelligence. The past 4 years now, can you just give us your perspective? Like, did you see this coming? Did you expect it to be what it is today as quick as it was? Kind of give us an idea of your perspective of the speed that this has kind of moved from where it was to where it is now.
Yeah, so I think there's been 2 big accelerations. One was from 2012 onwards after ImageNet and that whole piece of work where suddenly image recognition tasks were getting superhuman performance. This is like ancient history now in AI. So you guys have probably all forgotten it. You probably were all in grade school when this happened. But this was a big deal at the time because AI neural networks especially had been kind of in a winter for a long time. And there was still a lot of debate about whether neural networks was even the right thing to do with AI. That moment, that ImageNet moment in 2012 was really kind of a kickoff moment for the scene. And suddenly these things were having superhuman performance. That was largely because of the availability of data as a result of the huge amount of image data created by and captured by the internet, and especially compute. Like suddenly we had enormous amounts of compute available at commodity prices, and that really is what sort of unlocked that. And that kind of unlocked that first decade, perhaps up until the ChatGPT moment, which was obviously the second massive moment. And I think that moment, I didn't honestly see that moment coming. And actually a lot of people I think in the field didn't see it coming, and credit to OpenAI especially for betting on transformers and betting on scale of transformers as really being a sort of a big unlock, because the transformer paper came out in 2017, came from Google.
Yeah.
But Ilya and OpenAI really bet very big on the idea of just kind of scale is all you need at some level. Probably scale isn't quite all you need, but you get a long way with that thought. And then productizing it, especially as a consumer product, with the first ChatGPT launch. I think that was huge for the field, and I think it was as much a product moment as it was an AI moment. Because of that, and because of the sort of billions and billions of dollars that have gone in investment, we're now at a stage where we really have some pretty useful systems come out of that.
Yeah, I want to come back and look at the big picture. Before that, let's dive into AlphaFold here. So, in layman's terms, explain what AlphaFold is, and then we can kind of dive in a bit deeper.
Sure. Okay. So the setting up the problem. The problem is the problem of protein folding, or specifically protein structure prediction. So the proteins are the spigots and the cogs and the functional molecules of the body, of all of life. And in every one of our cells, trillions of proteins are being generated and turned over every second, and that is what gives us our behavior, gives us our metabolism. That's what makes us go. They're structural, they're also functional, they're enzymes, they catalyze reactions. So these are kind of very, very important. It's very important in a lot of pathology and a lot of diseases. And proteins are essentially very large macromolecules, heterogeneous macromolecules. They can be, they're made of amino acids. They can be hundreds, sometimes thousands of amino acids long. And depending on their sequence, you have an alphabet of amino acids. 20 are used in life. And so you can think of them as very, very long sentences written in an alphabet of 20 letters. Depending on that sequence, they will fold into a characteristic shape. And that shape gives them their function. So this thing might be like the head, and another protein is going to latch onto it like that, depending on the complementary shape. So the shape of the protein is incredibly important to its function. And this problem of how you get from the sequence to the shape was a long-term unsolved problem. We used to do this by crystallizing the proteins, putting them in an X-ray machine, taking an X-ray from them, and then trying to solve from the X-ray what the structure of the protein was. Doing one of those could take a whole PhD to do that. There were some hard to crystallize proteins which took a decade to solve. Computational protein prediction had been around for a long time. It's been around since the 60s. In fact, our company, Dayhoff Labs, is named for Margaret Oakley Dayhoff, who was the first person ever to publish a program to predict the structure of protein, which she did in 1965, a great hero. And she was also one of the founders of the PDB, the protein database, which was the resource that really made all of this possible. But it was an unsolved problem, and it was a problem that, we happened to approach at the right time, with the right compute resources, and with the right people to kind of make a dent in that problem.
We'd like to take a quick break to highlight one of the sponsors of the Middle Tech podcast, Awesome Inc., the innovation hub in Central and Southern Kentucky. Awesome Inc. helps grow the Kentucky tech and entrepreneurial community through pitch competitions, a mentor-driven startup accelerator, the Kentucky Entrepreneur Hall of Fame, co-working, and the Team Alpha internships. Be awesome. Now, back to the show.
And so take us back to you're in an office, you're in a conference room, wherever with DeepMind, and there's probably all sorts of different projects you guys can try and tackle. How did that become the one that was greenlit? And at the time, like, how out there was the idea of being able to use something like neural networks to solve a problem like this?
Well, and also how many projects were on the docket to even consider going after that you chose AlphaFold up against?
So the AlphaFold project actually started in a hackathon. I think this is like testament to the power of hackathons, an internal hackathon within the applied group, which is the group that I was helping to run at DeepMind. I think that really is testimony to the fact of what you can do in a couple of days of concentration. We let the people in the team work on anything they wanted to work on. We did 2 days, cleared the decks, did it just before the weekend so people could kind of carry on working through the weekend. And 2 guys, Hugo Pedidones and Marek Barwinski, whose names should forever be remembered, decided that they would go after protein folding in a couple of days. And their particular idea was, there used to be this program called Fold It at Home, some of you may remember it, which was, I think was produced by Stanford. And it was essentially a computer game which was allowed, it was like citizen science. Like you can manipulate this protein and try and get a low energy structure out. And the first thing that we tried was to use reinforcement learning, which is what DeepMind was using a lot of at the moment to do the Atari games and various other things like that, to control this fold-it at-home computer game. And in that short period of time, 3-4 days, we kind of thought that we'd got results that were, they weren't great, but we thought these were not like crazy results. And it was kind of an interesting thing to approach. So the next thing that happened was I happened to be in Oxford that weekend, and I went to Blackwell's bookshop in Oxford, and I bought 6 copies of a book called Protein Structure and Function, which was our Bible. And I gave it out to the team and said, maybe we should think about doing something in this space. And then we started doing a little bit of research. Anyway, cutting a long story short, we ran it as a skunkworks project for about 6 weeks with 3 or 4 people. Didn't tell anybody we were doing it, just see if we could make some progress. Then we took it to Demis and said, we think there's something here. I think the thing that got Demis across the line at that time was the fact that there's this competition that happens every 2 years called CASP, the Critical Assessment of Structure Prediction, which is kind of like the Olympics of protein structure prediction. And it happens every 2 years. Lots of teams all over the world enter. Demis loves a competition. And because, you can enter it and you can win, and then you can get articles about it. So I think because of that, we decided, so this was 2016, the next CASP was going to be in 2018. So we started the team with the view to, let's go and see if we can make progress on CASP in 2018. And so Dennis said yes, and we started with 6 people. That first team grew to about 8 people. Then the second AlphaFold 2 team, which happened after I left, so I only worked on AlphaFold 1. That was probably about 15, 20 people, the second one as well. So it basically, and actually a lot of stuff at DeepMind happened that way. It grew by success. It started with a very small team, see if you can make a little bit of progress. You make more progress, you get more resources.
At what point does it become a breakthrough? At what point did you say, okay, this gets us in the running for something like a Nobel Peace Prize? Like, at what point were you like, wow, this is different level?
So I think partly other people would need to answer that, because that would be the AlphaFold 2 and the AlphaFold 3 people. But from the AlphaFold 1 point of view, I mean, it took us, I'm going to say, about 9 months just to get up to the state of the art in the field. So at that time, the state of the art was, if you took an unknown protein which hadn't really been seen before, and you could try to predict it, you could get a rough prediction about 45% of the time. That was and then AlphaFold 2 took that to 95%, which is basically the same as the error you get if you crystallize it. AlphaFold 1 took that from 45% to about 65%. So it took us about 9 months to get to the state of the art. And then I think in that project, the breakthrough, there was like this one weird trick to solve protein folding, was most teams were working by just predicting what's called a contact map, which is how are these 2 residues, are these 2 amino acids in contact with each other, or are they not? And if you can predict all of the contacts, then you can sort of predict the fold. We decided to predict the contact distance rather than just whether they were in touch with each other. And that extra piece of information kind of got us to the next level. So the first one, it was really just that trick. I mean, it wasn't quite, there was a lot of data engineering, and you have to be very careful about how you do this in a lot of ways, how you use the data that's available. But it was definitely, that was one of the things that kind of got us to that next level. And then the AlphaFold 2 and then again AlphaFold 3, basically complete rewrites of the system from scratch and sort of tear it all up and start again.
And can you kind of help us frame how significant where we are now with AlphaFold 3 is? So correct me if I'm wrong, but AlphaFold 3 is now able to predict the interactions that the proteins are going to have, I assume, with different proteins. And I'm not super versed on this, so maybe you can explain a little bit better than that. But tell us, where does this take us from here? And maybe we can get into, I know you're not involved with isomorphic labs, but we can talk about what drug discovery means and kind of on down the road.
Yeah. So, being able to predict the structure of these proteins, and, the structure is very closely related to its function. So if you want one protein to interact with another protein, it needs to have some kind of complementarity to it. A lot of drug discovery is making a molecule, usually a small molecule, that will interact with a protein and either modulate it up or modulate it down, or correct some deficiency with the protein, because a lot of disease pathology is some deficiency with the protein. And so having the structure of the protein is step one, but what you really want is, you want to know, if I take this other molecule and I dock it, I interact it with this protein, what will happen? So that's the interaction model that AlphaFold 3 and other models like Boltz 2 now we have as well, and Chai for discovery as well. There's now like maybe a dozen open source models which are pretty close to the AlphaFold 3 level as well, which are now getting into this domain of not just give me the structure of the protein, but give me the structure of the protein docked with this other molecule, which is my medicine molecule. So that will tell you, is this medicine going to work? Are there going to be side effects? Is it going to be easy to get into the cell? All of those kinds of issues. But the problem is definitely not solved, right? There's still lots and lots of classes of molecule that we don't do very well on. Actually, protein-protein interaction is very difficult, because that's usually not just about shape, it's also about the electronic structure of the protein and how those two things match up against each other. So that's still very difficult. So for things like monoclonal antibodies and so on, there's still like lots of challenges. So there's still a lot of work to be done.
I was going to ask about the development environment around this. You mentioned open source there. How much of this is the cutting edge living in open source versus closed source and owned by entity?
It tends to be the case, as with actually all of AI, not just AI in this space, that the initial breakthroughs often are very expensive to train and require a lot of resources. Those resources usually live in private labs. Some of the private labs do make their stuff available open source, some of them don't. But very quickly after the frontier model comes out, you will find 5, 6, 7 teams reverse engineering the paper and producing a version of it which is open source, and usually like 10 or 100 times more efficient in terms of its compute requirement, and the size of the model as well. So that happens again. I mean, it's kind of what everybody saw with DeepSeek, right? There's sort of the DeepSeek pattern, but within molecular modeling as well. And that's basically the law of AI. It's like big model comes out, takes a lot to produce, very quickly, an open source version that takes 1/10 of the time to train or 100th of the time to train comes out, which is maybe not quite as good as, but it's probably 95% as good.
Can you talk to us a little bit about the acceleration of this type of technology as well, AI in general, but being able to have access to open source models like this? And it's almost like we're building kind of the foundational building blocks that we might start seeing other AIs be able to leverage what's being done, what's kind of come before them. You're starting to hear a lot of talk about our AI is going to be able to do science for us, make new discoveries for us. And I feel like technologies like this are going to play a critical role in that. So I'm curious if you have an opinion or a thought on that side of things.
Definitely. I think that whole area of AI for discovery is, there's going to be a lot of that in the next 5 years. We're going to see a huge amount of that. There's been some really interesting kind of prototype projects already in that domain, combining, the LLM models with some of these more sort of specific functional models, molecular models like AlphaFold, or there are other models in chemistry and materials discovery, et cetera. There's a really interesting group at Stanford in James Zhao's lab who made this system, which is basically 5 or 6 different LLMs interacting with each other, like they're having a lab meeting. And each one takes a different role. There's like the discovery scientist, there's the critic, there's the process engineer, there's all of these different roles that you might have in a lab, as well as the human scientist who's working with them. And they use that system to design a new nanobody for an antibiotic, for a delivery mechanism for an antibiotic. And there's a similar project at DeepMind, there's a similar project at MIT as well. So I think this model of multiple AIs working together with the specialist models to work as a team towards a discovery is really important. But what's interesting is, to make it impactful, discovery is only one step. You've actually also got to know that it can be made, that you can actually get it into production, that you can do it at scale, that you can do it at the right cost, that you can do it with all the safety around it as well. So that's actually, discovery, if you like, is only step one. We've got like 9 other steps we've got to solve as well. Part of what we're working on at Dayhoff Labs is kind of putting that whole picture together.
Yeah. Well, that leads to kind of one of the questions I have, which is how does this affect aging and longevity? Do you have any projections that are in your community that are being put out there about, how that affects, somebody like me who's about to turn 30? How old can I be?
I think that's already there. We already have huge advances in that area, and some of that is AI related, but a lot of it is just the science is getting really good in that space. It's not a domain that I'm an expert in. I probably should be more of an expert in, given my age, but I'm not really an expert in it. But it's definitely true that we can now spot markers of the big aging diseases 10 years, 20 years out now. Whether that's neurodegenerative or cardiac or oncology, there are clear markers that we can find a long way ahead of time. And we can make interventions. Most notably, we can make lifestyle interventions. I mean, the basic idea is that the lifestyle interventions work, right? You do the things that they tell you. You know, you're going to stay younger longer. But there are also now these increasing kind of medicines, the GLP-1 agonists, the metformins, etc., which we know in combination with certain risks will lower your risk of this over a long period of time. So I think we already have the science to make a huge difference on the aging side. We have more of a challenge about how we operationalize that, because reimbursement doesn't work very well for that kind of model of like, I've got a slightly elevated risk 20 years out, so I'm going to go and like take this medicine for the next 20 years. Does that really work? That's more of the challenge. Is like, how do we make this work at a society-wide level rather than an individual level?
Yeah, I think what I get really excited about it when I think of that field as somebody who is still, relatively young, is moving from healthcare that is more reactionary to my symptoms to more preventative and being more customized and personalized.
Yeah.
I think that is something that I get really excited about that for myself, because I think it's pretty close, but I also get really excited about that for my kids.
100%.
Yeah.
And I think, again, like the reimbursement model and the insurance model, how's that going to work? That's probably the bigger problem rather than the science model. But we already know, for example, like LLMs, again, it's not even close. LLMs are much better diagnosticians than MDs. There's multiple peer-reviewed studies now which show this across all kinds of different symptoms areas. And to me, that means I want, the doctor in my pocket, the LLM doctor in my pocket, which, by the way, is also connected to my real doctor, which has full access to my entire history, which knows how much I walked today, which knows what I'm eating, which can do all of this preventative stuff. And I think that is probably how it'll happen. We'll start to see startups, by the way, go start some startups to do this, because I think this is like a really strong area, which make this as a consumer product. Like, so this is like, essentially the person looking after me in my pocket all the time.
Yeah, I think I want Evan to get us into DeepMind here in a second, but my favorite piece of consumer tech that I bought recently is this Oura Ring that tracks all my steps. I wasn't sure if I'd like it or not, wasn't sure if I'd want to wear a ring, but one, I don't notice it's on, it stays charged for 5 days, but it tracks so much data. I feel like this is a form factor that would be perfect for AI, especially around health and everything, because it tracks my sleep, it tracks my walking, it tracks everything, except I guess it can't track what I eat yet, but I mean, it's not that far. But Evan, why don't you get us into DeepMind here?
Yeah, I mean, let's go back macro here. DeepMind sold to Google. Can you walk us through why that decision was made versus staying independent, given OpenAI stayed independent, Anthropic? What did Google give maybe DeepMind that they didn't have at the time that made the acquisition make sense? And then I want to kind of take a step up and talk about the dynamic between the different labs and providers of large language models and how they're all interacting and the differences. But start with that acquisition.
Yeah, so let me caveat this with the fact that I wasn't actually involved directly in the acquisition. I came over to DeepMind after it had already been acquired. I did help them integrate a little bit into Google in those first months, but I wasn't involved before the acquisition. As far as I know, the acquisition happened in 2014, like early, so February 2014. It's like the dark ages in AI time, right? And astonishingly, Demis found it very difficult to get DeepMind funded. He set out in 2010, 2011 to build a company with the explicit goal of making AI, making artificial general intelligence. So, fully general intelligence, which at that time was like a crazy idea. And it was not straightforward for him to get funding. And it was not straightforward that he was going to be able to generate ongoing funding, et cetera, as well. So I think that was probably part of the reason, was that actually doing it inside of one of the big tech companies was a better proposition. I think, in fact, I'm pretty sure that over the subsequent 5, 6, 7 years, there were many moments where he arguably regretted that decision, especially when he saw the kinds of funds that were going into places like OpenAI only 3, 4 years later. But at that time, it looked like a really good deal. And although the acquisition price was not all that much, it's not public figure, but people have said it was like $600 million for the acquisition, that they were then very quickly spending probably $1 billion on the company every year after that as well, in compute and, costs of personnel, et cetera, et cetera. So it was almost like Google was a big investor into DeepMind. And certainly for those first, I'm going to say 6-7 years, stayed pretty independent of the rest of Google. Now, we can argue about whether that was a good idea or not. Maybe that was one of the reasons why, OpenAI did ChatGPT, not Google, despite Google inventing it. But it was, for that first period of time, it very much felt like an independent company with, a big investor called Google.
Yeah. And there are plenty of startups now leveraging large language models. There are all kinds of new emerging use cases. And you are an investor, you look at AI companies regularly. Are there applications or use cases or qualifications that exist that you say, this is somewhere large language models should be applied? So obviously the ones that have taken off so far are the Cursors of the world.
Yep.
And apps like that where it's a lot of development, something that's provable, verifiable, and can be iterated on with the large language models. There's a lot of context there. So what are some things maybe you look for in a startup that's leveraging these technologies and the qualifications for those?
Yeah, certainly. Obviously, the data is really important. Like, can you leverage a large amount of data? Do you have some kind of privileged access to that data? Or through the usage, can you generate more data that you're going to have privileged access to as well? Because that's sort of part of the defense there. But I think it's also very much, it's now very much, I say this a bit as a product manager, which is what I historically have been. I think it's very much a product story. Cursor was successful because they were not the only people who've been integrating LLMs with IDEs, but the particular way that they did it, caught on, and they've been very successful out of that, and created insane revenue growth in a very short amount of time. And I think we're going to see that again and again in lots of different fields. It's like, okay, what's the right form factor? I think about this in science, our users are scientists. What's the right way for us to fit in with their workflow? What are the tools that they're already using in their workflow? How can we fit what we do into their workflow in a way that makes sense to them, in a way that they're going to love, in a way they're going to sort of get really angry with us if we take it away from them? That's really how I think about it. And I think that's true across any field. It's like, okay, how do you integrate this capability into the user's workflow in a way that's natural for them? And I think we're right in the early innings of that. I think there's a huge amount of work, product work, to be done on that in the future.
And I guess the one thing that, I'm a founder of a company that's doing just this for a use case that is request for proposals, very complex use case. And one thing we're always wondering and we're trying to watch is what's the form factor of the user interface going to be, and how much does human need to be in the loop? And agents is the talk right now. Yep. How much of the UI or the interface that we're used to dealing with software do you think gets abstracted away by agents, and how should founders be thinking of that dynamic of what do I show, what do I leave up to the agent, especially as they improve and you have mixtures of agents working together? How do you look at a startup and say, is this the right approach? How do you think about that?
I think that's a pretty good question. I think that in the next year, 2-3 years, user interface is still going to be incredibly important. We're not going to be in a sort of world where it's just agents talking to each other over APIs and we don't have to worry about the user interface. I think it's going to be an interesting question to think about what's the best way for agents to talk to each other. There's already a lot of research going on in that domain as well, and that's not an obvious problem. It's not obvious that the API that you or I would use as a programmer is the perfect API for an agent to talk to another agent. I think there's some really interesting research work going on there. But given the state that we're at with the capabilities of agents, I think in the near term we're definitely going to need humans to be part of the story, and that's going to mean software that we can use as humans. And again, all of the things that make great software now are still going to be true. Is it usable? Is it easy to use? Is it delightful to use? Does it get my job done quickly? Can I understand it? Does my mental model of what's going on here, is it consistent? Can I become an expert quickly in this software? All of that is what's important, I think.
I want to zoom out to kind of just this period of history that we're in that's going to be talked about for a long, long time. When you think of the direction that artificial intelligence is heading, and just this, we have this new thing that could be compared to the internet, to electricity, that's now going to permeate basically every part of our lives. What excites you, and what scares you about it? I mean, like, where do you fall in terms of, I'm more excited about this versus I'm more nervous about the implications of where things could go wrong? Where do you sit in that spectrum?
I think I'm very much, in the middle of that, like both excited and nervous. There are a lot of questions. It's a time of big change, not just through AI, but for all kinds of other reasons. And those times are challenging. It's challenging for us to catch up with what's going on in the world and to sort of develop our own models of how to deal with it, how to plan for the future as well. No doubt that's challenging. That also makes it very exciting. Also means that there's a lot of opportunities have opened up. So I think I'm pretty much in the middle of that. But I don't think I have any more insight probably than anybody else does on that. I think we're all faced with these changes, and we're all going to have to work out how to deal with them together. Some of them are very positive. I think for science, it's very positive. I think we're going to get great medicines out of this. We're going to get great materials. We're going to be able to do make things that we use in the material world much more efficiently than we used to be able to do. Maybe not burning so many hydrocarbons to make everything everything on this sofa and on this. Well, actually, no. Some of this is mined, but there's probably a lot of this that comes out of the petrochemical industry. Maybe we're going to be able to do a lot of that a lot more effectively and efficiently than we were before. But we're definitely going to get challenges of not necessarily unemployment, but big changes in the world of employment. We've got big challenges which we've already had for a decade or more about algorithmic manipulation, and that's only going to get bigger. So yeah, I think there are a lot of very positive stuff. There is also generally a lot of challenges. I think I'm fundamentally an optimist. I think especially in democracies, I think democracies in the end are good at dealing with these complex challenges. It's rough along the way, but I think I'm long democracy. I'm not one of these people who thinks that China's got the right model, and we should all be like dirigiste from the top. I think in the end, democracy is robust, and I'm long democracy.
To that point, there's a book that I'd recommend to anyone here. Maybe you've read it, The Evolution of Everything. It talks about that exact principle of all the most enduring things that we take advantage of now. Democracy, currency, markets, all of it is ground up. It's from the ground. It evolved. It evolved. It was not top down imposed. I think that's the same thing. Do you have anything else before we kind of?
No, I think we should turn over to the audience here. I guess one last question, as somebody that's at the intersection of science and biology and AI. I think an interesting topic that tends to come up frequently for me when I talk about AI with friends or peers is how much we're trying or incidentally replicating what goes on in our brain.
Right.
With AI, and especially the large language models, the architecture of these. And somebody I was with coffee with this morning said, well, an AI app is really all about just taking something you've seen before as context and applying it the next time. And that's how you get, a unique outcome, or you get the right answer. Isn't that what our brains do? Anyways, with creativity, we see things in the world, we react to them, they leave impressions with us, then we mix them together, and then we have a new output. And so how much of what you see with maybe your understanding of the brain and what's going on with large language models, are we going to get closer to understanding, what some of these big underlying questions are about how our brains work?
Understanding ourselves.
Yeah.
That is a good question. Also, I'm also not a neuroscientist. I should say. I mean, I've hung around a lot of neuroscientists, but I'm not a neuroscientist.
What are they saying?
I mean, I think the first thing is like we are predictive machines. Like our brains, we are constantly predicting the world, and we're constantly adjusting our prediction of the world depending on the information that comes around. So in that sense, we're quite similar to these AIs, but we don't do it at all in the same way that transformers are doing it. So, it's definitely true that what we're doing to manifest the intelligence that we have is not at all the same as what's going on in the machine. We're not, predicting the next token in the same way as the machines are. But there is probably some read across between the two. There are some things that we can learn from both sides. And indeed, interestingly, a lot of interpretability work. So, one of the things that everybody may know is that we don't have a great handle on actually how these things are able to do the complicated stuff that they can do, how they can do this sort of simulacrum of reasoning, answer complicated questions, apparently be creative, be friendly, be unfriendly. We don't really have a strong sense of how they do that. So there's a whole field called interpretability, which is about how do we understand what the models are doing. And that's using techniques which are quite similar to the techniques we use to understand the brain. It's like ablation studies and, what happens when these neurons light up and those other neurons. Anthropic have done some really good work on this recently. So I think, although I don't think the two systems are working in the same way, we can probably learn something from the way that we try to understand our brains to understand these new black boxes which are capable of complex behavior, which is the LLMs. And I think that's very promising. I think we'll understand that a lot better in the next year or two than we have before.
One last question here before we turn it over to audience questions. You've worked on all this incredible stuff throughout your entire career. You're now working on Dayhoff Labs. Can you just give us kind of the quick version of what you guys are doing, high level, as much as details as you'd like to give?
Yeah, we are. So Dayhoff Labs, we're founded on the idea that living material in the universe is the primal example of how complexity emerges from apparently, a random set of atoms, chemicals, whatever you might call it. Understanding that process is key to us understanding all of this other stuff, including intelligence. And it's also key to us understanding how to synthesize materials more effectively than we can right now, and eventually to compute more effectively than we can right now. So that is the problem that we work on, is really kind of using these techniques to understand complex chemistry and biochemistry and the difference between those two things.
Super interesting. All right, we'd like to turn it over to audience questions now. If you have a question, raise your hand, stand up, ask it. I'll repeat it into the mic, and then go from there. Just so we capture it on the podcast, asked about the architecture of AlphaFold.
Yeah, so the first thing to say is that the architecture evolves in each iteration. So each iteration is different from the previous iteration, notably different. So AlphaFold 1 was very different from AlphaFold 2. AlphaFold 3 is different from AlphaFold 2. And indeed, I mentioned all of these other open source projects that are out there now that are doing similar things. Many of them have got very different architectures from each other, but they get to the same place and the same goal. To answer specifically about AlphaFold, AlphaFold 3, the latest version of AlphaFold, is a combination, or it's very much neural rather than symbolic, but it's a combination of really a transformer-like architecture, so an architecture that is similar in some ways to the LLM architectures, which is focused on the sequences of the proteins, and a diffusion model kind of architecture, which is similar to the image generation models that we see, which is focused on the generative aspect. So that is like, given this molecule, how can I generate another molecule which is gonna bind to that molecule? Actually, the first people who published on that using that technique was not DeepMind. It was David Baker's lab at UW. David Baker, who also won the Nobel Prize. And But yeah, AlphaFold uses that techniques. There are others that are pure transformer ones that only use transformers. So the ESM family of models from Meta, for example, they're just purely sequence-based models. So there's a variety of different approaches, but they're all, very much kind of large or very large neural networks. Interestingly, they're not as large as the LLMs. So LLMs, trillions of parameters. A very big molecule model is probably 1 billion parameters. And the ones that we work with are like 100 million, 200 million parameters. So they're not huge by LLM standards.
Vern?
Yeah, so I think the question is like, given that these things are black box methods, how do you, explain it to wet lab scientists and convince them that actually the prediction is a real prediction? Right now at Dayhoff Labs, I don't have to do that so much because everybody inside the tent is kind of bought into the idea and gets it. We do have people who are wet lab scientists as well as AI scientists. But even then, the predictions that we make, let's say we're trying to find, design a molecule for a particular function. And we might come up with, you usually don't get one design, you usually get like a whole set of designs out. And they're usually ranked as well. So, you'll go and look at the top 10 designs that you come out with. You'll go and do other work as well. You'll do some docking work. You'll go and look in the literature. Is there homology in the literature that's near to this? So you'll build up a package of evidence because you're not going to go and you might get 100 predictions. You're probably not going to go and do 100 assays. You're going to try and pick out the best ones, and so you're going to try and say, okay, this one sort of makes sense. Number 3 makes sense because I can find evidence for it in the literature as well. So there's still a bit of back and forth there as well, which also helps to build conviction. But ultimately, we have to go and try it. I mean, it's not real unless you try it in the lab and you show that it's real. Eventually that's the answer. I think there's still a bottleneck about data, right? We still, actually in biochemistry, we now generate a huge amount of data. So it's not the raw amount of data, it's more organizing the data into a way that can be used for AI. In chemistry, we have a genuine lack of data. So we've got to solve the how do we generate more data in chemistry problem before we can really get into that. And that is very much an engineering job. Both of those things are engineering jobs. Data management, data engineering. In fact, they used to say, and this is really true, applied AI turns out to be 95% applied and 5% AI, right? In other words, like it's the data engineering. And in the original AlphaFold project, the first 9 months, we basically just did data engineering. That's all. Like getting the data into the right format, making sure that we didn't have contamination between our training sets and our test sets, all that stuff. So I think bringing that engineering mindset to biology and chemistry, that's probably the cultural thing that has to change over time. It's like not just I'm sort of using my own intuition, but how can I, instead of thinking of my job as doing the discovery, my job is how can I make the tools to make the discovery more easy and make those more available. And that's sort of a cultural switch. I think that's happening, but it's definitely better now than it was 5 years ago, but it will still take time, I think.
All right, we'll have time for one last question. Go ahead, Lamar.
Yeah, so I think the question is about what other spaces are like really interesting from an investment point of view within AI. I think the first answer is that there is a huge variety. So like you can see opportunities everywhere in the application of AI technology to lots and lots of different domains. The first things that we've seen, I think, a lot of them have been text-based stuff. Areas where there's a lot of text that needs to be processed and where that's a really gnarly job and where you have a lot of people going through a lot of documents to make a lot of decisions. Maybe they're going to make those decisions badly. Maybe it's going to take a long time. It's just a horrible job. All of those are really great domains. So RFPs is a great domain. Regulatory filings for medicine companies, that's a great domain. That sometimes can take months and months and months to do a regulatory filing. You make a mistake in one of those, it can cost you $100 million because your competitor gets there before you do. Legal contracts, all of these kind of domains where there's like just a huge amount of text that's got to be processed. Those are all really great near-term opportunities. I mean, coding is another one, right? Great near-term opportunities for LLMs and AI. But I think that's probably only the near term. I think we'll see many different domains over time.
All right, I want to close this out with one final question here, just forward-looking, futuristic thinking, which I know is really hard to do with how fast everything's moving. But if we fast forward 5 years from now, what breakthrough would you bet on that most people underrate today?
Great question. I think it's a bit of a technical answer, but I think I'll give you one that's I think underrated and one that's overrated. So I think underrated is going to be the use of simulation in science. And again, simulation is something that's been around for a long time. We've been sort of simulating molecules and their interactions in computers for decades. But we're now at the point where the cost curves of doing it in the lab and doing it in the computer are starting to cross. And that's been driven by the same driving down of costs that's been driven by AI and GPUs. So people are kind of porting all of these codes to GPUs. Plus AI is also making that world of simulation much more efficient. So we're able to simulate systems that are much bigger than we could even 5 years ago. So I think that trend as a data generation trend is underrated and is going to be really big over the next few years. So simulation, generating data in simulation, that's my long. My short over that time period is probably quantum computing. I think that the number of, first of all, quantum computing I think is still far enough out that we don't know how far out it is. And secondly, the number of things that were reserved territory for quantum computing that it turns out that we can do pretty well with AI is going up all the time. So yeah, I'm long simulation and short quantum in a 5-year frame. 10 years, maybe different.
Awesome. Well, thanks so much, Steve, for joining us. This was an awesome conversation. Everyone, please join me in thanking Steve for taking time out of his visit to Kentucky to talk.